with impulse. And I want to start by basically defining momentum and then what impulse is. And I want to make some comparisons between the unit we're looking at now and the unit we had before. Okay? So first, and we didn't, all right. So here's my definition for momentum. I define momentum as inertia while moving or inertia due to motion. That's kind of my headcanon for what momentum is. What it states is that when an object's moving, its inertia changes. The more it moves, the more inertia it has. If you don't remember what inertia stood for way back in the first part of our class, let me redefine it for you. Inertia is an object's resistance to changes in motion. That's what inertia is. So what we're saying here is that momentum is another way to measure this resistance to changes in motion. Now, technically, momentum is just a product of two things, mass and velocity. We use a lowercase p for momentum because I guess other stuff was already used. So lowercase p. And it's got the bar on it because momentum is a vector quantity. Unlike energy, which we got to remove the bars from everything because energy was a scalar, momentum is a vector. So that is important because it plays a huge critical role in how we deal with the momentum and vector portion for things like collisions and impulse. So I want you to be very clear. Start putting those bars back on things that are vectors to remind you that you have to take direction into account. What that suggests to you is that anytime you have a momentum problem, you need to choose which direction you call positive. You'll remember we didn't have to do that for energy. We just set a reference level and everything was positive from that point forward. We said things like positive work increased something's energy and negative work took it away. That's not the case here. So when we talk about momentum, positive for momentum means the direction it's traveling. And negative for momentum would mean the direction it's traveling. So if you set to the right to be positive, then you get an answer that's to the left. That means the object probably bounced off and went to the left after it collided with something. So positive and negative have meaning here. We need to make sure we're careful. Now, I'm going to make lots of comparisons to the unit we just studied so that we can kind of see how they are similar and how they are different. But I want to start by talking about some simple stuff here, like the units. The units here are kilograms, meters per second. There's no special name for that. So we have units here, and you're going to put an answer that has its units, kilograms, meters per second. And you don't have to call it something else or nothing like that. Also, because momentum is a vector, it gets its vector direction from the velocity, which I think makes sense. So whatever the direction it's moving, that's the direction of the object's momentum. But again, I say that it's an object's inertia due to motion, which means that the faster an object moves, the more momentum it has, the more difficult it is to change the object's motion. Now, we have another measurement that looks a lot like momentum, and it's kinetic energy. But these two things measure different things and tell us different things about the object. The first thing I want you to kind of put into your notes to make sure you have at least a reference to this, you actually need both of these to figure out what an object's doing. Energy doesn't contain information about direction, but it talks about how the energy has been moving from one form to another. So energy has value here because it tells us a lot about how or where the object might be or where it's going. Momentum, on the other hand, has direction. It tells us what direction the object's moving. It also tells us the direction of the motion of the center of mass of a system. This is a group of particles. But also, kinetic energy was very velocity forward, right? Small changes in velocity made big changes in kinetic energy because it was squared. Momentum is more mass forward, right? Mass is on equal footing with the velocity. So changes in mass are just as important as changes in velocity. That's because this one is about inertia. It is the central part of what momentum is about. Now, changing momentum requires an impulse. Impulse is how you change something's momentum. Again, an impulse has a lot in common with work. If you remember, work is how you change something's energy. Impulse is how you change something's momentum. In fact, impulse is directly defined as the change in momentum. Work was not defined like that, but net work was, right? Work is something that one force does, but net work was what the net force did. So if you do net work on an object, then you can change its kinetic energy. You guys remember that? So these are similar. Now, if you remember, net work is the net force times the displacement, taking into account the direction. Right? Do you remember all of those parts? So we had to apply an unbalanced force. The object had to change location because of that unbalanced force, and we had to take into account the direction between the unbalanced force and the displacement. It was somewhat complicated. Impulse is similar, but with a little bit less complication. It is net force, but it just involves how long the force is applied for. So impulse has two parts, the cause and the effect. Now, I bring this up because some of the simplest multiple choice questions become confused because of the language they use. So, if I tell you that the object is traveling at 5 meters per second, and then it's traveling at 2 meters per second, and I say, what is the impulse applied to the object? You might think, well, they didn't tell me anything about force and time. Remember, impulse is both of these. Impulse is force and time, or its change in momentum. But I know from history that you seeing this doesn't always translate into the possible ways you could write that. For example, this is P final minus P initial. Right, that's what delta means. And momentum is mv. So this is mv final minus mv initial. All of these represent the same way of writing change in momentum. They are the same thing. So that's what I mean when I say you can see a problem, a multiple choice question, asking about impulse, but giving you velocity. Well, they're giving you the stuff to calculate the change in momentum. And that's what they mean by impulse, calculating the change in momentum. Now, of course, they could give you a 20 Newton force pushed on the object for 12 seconds. You would have the impulse because you would know the force and you would know how long it acted on. And there's nothing fancy here. This is just regular old multiplication because time is a scalar. So the direction of the impulse is the direction of the net force. All right, now look, there's like 5 of you. You guys are all falling asleep. I want you to pay very close attention here because you guys are easy to trick. And it's because it's the afternoon, you're tired, and you just want to go home. I get it. It's Monday. So imagine we're looking down on like an ice hockey floor, and the puck is moving to the right. And then somebody hits it with the hockey stick, and suddenly the puck is now moving this way. Now, I'm bringing this up because even if it's the same size speed, say this is 10 meters per second, and this is 10 meters per second, did the object's momentum change? And the answer is yes, it did. Even though the number part is the same, is it clear the direction part is different? Because momentum is a vector quantity. But you'll notice the direction of the momentum at the start of the problem is to the right, and the direction of the momentum at the end of the problem is upwards. You guys see that okay? So when the stick hit the puck, it had to apply a force. Did it apply that force this way, this way, this way, or this way? 1, 2, 3, or 4. Hold up which finger best matches the direction of the force on the puck. The force occurred right here. It caused the change. Okay. Try to get an idea for what everybody's ideas are. All right. First, I want to remind you that a force had to be applied to get the puck to change direction. That force had to stop the motion that is to the right and cause motion that's upwards. So all of you who said that 1 was the correct answer, if you had only pushed upwards on the puck, then the puck would be going this way because you didn't stop it from going to the right. So that wouldn't work. The correct answer is 4. Because 4 is going to stop the puck from going to the right. You notice there's a component of that force to the left, and there's a component of that force upwards. So this next part is going to illustrate this. Impulse has its own direction. And the direction of impulse is the direction of the net force. It is in the direction, bless you, it is in the direction of the change in momentum. So in order for the puck to go from to the right to up, it had to change in this direction, stopping the motion to the right and starting motion upwards. So the direction of impulse is how the momentum changes. I'd save this for the end of class in 6th period, but I think we'll do it right now. Because I think you just need to try something, okay? You may want a calculator for this, but it's not going to be particularly hard numbers. Let's say you throw a ball at a wall. A ball has a mass of 0.5 kilograms, and the ball is thrown at 3 meters per second. The ball hits the wall and then bounces off the wall this way at 2 meters per second. Okay? Can you tell me the impulse on the ball from contact with the wall? Try. So the answer is 2.5 kilogram meters per second to the left. Do we need to work it out together? Okay. Do you want the right or the left to be positive? Okay, so we are setting the right to be positive. That suggests when I get to this one, using it, I'm going to have to make it negative because it's moving to the left. So I asked for the impulse. Impulse is either force times time or change in momentum. Which do we have information to use? We have information for change in momentum because we have the final and the initial velocity, and we have the mass of the ball. So I'm going to do mv final minus mv initial. Well, this is negative 1 minus 1.5, or negative 2.5 kilograms meters per second. The negative sign is about direction. We stated to the right was positive, so this negative sign means to the left. So tired. Aww. Sad babies. Tired, need naps. Now, the change in momentum is to the left. What is the direction of the force on the ball? Not trying to confuse you. Also to the left. The change in momentum has to be in the direction of the force on the ball. So the wall had to push this way on the ball. Does that make sense? Now there's excuse me. There's an equal and opposite impulse on the wall. So the wall experienced an impulse of 2.5 kilograms meters per second. But it was not, yeah, to the right, but it was not particularly effective at moving the wall. But the wall still experienced the impulse. This is not like work, where if the object didn't change location, it doesn't experience the work. In impulse, it's just force and time. So an object can experience an impulse and not be moved by that impulse. That happens all the time. I'm sure you have thrown a ball against a wall and it's not moved very much. Well, that's what's happening. Now you might hear it on the inside of the wall because it moves a little bit and it creates sound. But generally, you probably didn't move the wall very much. Now, I'm not actually done with this question. This part's, I think, what you should expect to see on the second part of the question, which is if the ball is in contact with the wall for 0.003 seconds, how much force did the wall apply to the ball? Do you see a direction of what you're going to do to get this answer? Because you have the impulse and you now have the time. Okay. Can you do it real quick? Good. You're going to get a ridiculously big number. So net force times time equals negative 2.5 kilograms meters per second. So we're going to have net force times 0.003 seconds equals negative 2.5 kilograms meters per second. That's all it is. So what's my big number here? It's got to be huge. 833? Now, we're taking kilograms meters per second, dividing by seconds. So that's going to give us kilograms meters per second squared. And our answer is negative. It's to the left. Not terrible. This kind of stuff is just plug and chug kind of things. All right. I want to go on. Am I good to go on? Why do you always do that, Betty? I have to go on. We can't just stay right where we are. I might abandon you. So this next thing I want to talk to you about is something that I think is going to be a little tough for you to understand, but I'm going to try and do my best anyways. This is our definition of impulse. It's impulse equals change in momentum. And remember, both of these are the same thing. This is cause and effect. I want to divide both sides by delta t, though. Okay? Because if I do that, I get net force equals delta p divided by delta t. Now, you should also know that this looks like Newton's second law. It doesn't look exactly like you would expect for Newton's second law, but Newton's second law said net force equals ma, correct? The truth is, this is what Newton wanted people to know. He didn't want this. He didn't actually create that function. He knew that was an implication, but Newton's second law actually is the rate of change of momentum. That's the way Newton's second law was originally stated when he was trying to formulate his idea of physics. He elevated momentum to be a very important quantity and put it in the most fundamental law that he had created, because he believed momentum spoke more about what was happening to our system. So most of his work is about momentum, not about objects that are point masses, as we kind of did this. It's because he believed in other ideas that were a little more powerful. What happens when mass changes? What happens with inertia as an object experiences a force? But this also tells us some things, and I think these things are subtle and not necessarily easy to understand. First, one of the things it tells us is that if we graph momentum and time, the slope of this line equals net force. So if you're confronted with a graph that has momentum and time on it, they're giving you more information. The slope is the unbalanced force acting on the object. I know that you're going to say, that's new, but it's not as new as it should be if you think of it this way. We already have done graphs that have velocity and time on them. And what's the slope of a velocity versus time graph? Excellent. You're the best class for that. Notice what you get here. Do you see the similarities? If I multiply this graph by m, I get this graph. Do you see what I'm saying? So they could give you this graph and say, find the acceleration. And they're telling you to find the slope and divide by m. That's what they're telling you to do. They could give you this graph and say, find the force. And they're saying, take the slope and multiply by m. If I were you, I might write a few of those things down and study that. I think graphs on the test are the ones that are going to be the easiest to do if you know what you're supposed to do. So I'll say it again. These two graphs, they're very closely related. The slope of the top one tells you net force. The slope of the bottom one tells you acceleration. I'm being patient because... So if they give you this a momentum versus time graph and ask you to find the acceleration, they're saying find the slope and then divide by the mass. That would give you acceleration. But if they give you the velocity versus time graph and ask you to find the force, they're saying find the slope and multiply by mass. So there's information in here that's a little hidden. Now, that being said, and considering the similarities between these two, please also consider this next one and be very, very, very clear in your notes. This side. We have two functions that are very similar. Right? Two functions that are very similar. You may not know this from what we've done in the past, but we have often found the area of graphs, and the area of graphs have meaning. So here's two graphs. One where we take net force and displacement. So this will be places like, positions. 1, 2, 3, 4, 5 meters. So this will be something in meters. Or net force and time. So this would be something in seconds. And let's say they give us some graph. Doesn't matter what the graph is. These two graphs actually have other information in them. The area of a force versus time graph is impulse. It's change in momentum. And the area of a force versus position graph is net work. Change in kinetic energy. These are very similar graphs, and they tell us very similar things. But obviously, when doing your work, be careful. All right, you guys got that down? Okay. Now, in order to follow this line of reasoning, there's a bunch of things here that I think you guys should be able to do. For example, would you agree that no matter whether I drop the cup on top of the carpet or the tile, the cup's eventually going to come to rest? Does that make sense? Now, it might break, but the pieces will come to rest. True enough? Now, this part is the part that students tend to forget, and this is where I want to make an emphasis. If I start both cups from the same height, is it clear to you they will hit the ground at the same speed? All right, is it clear to all of you? Okay, I'm not trying to trick you. mgh equals 1/2 mv squared, right? So as they fall, they convert that potential energy into kinetic. If it's the same height, well, then V equals the square root of 2gh. So they're both hitting the ground at the same speed. Now, it's important that you know that part Because when they do make it to the ground, they both will have the same speed and then be brought to rest by the ground. So which cup likely breaks? The one on tile or the one on the carpet? Tile. Which cup experienced the greater impulse? So here, I was trying to lead you to this answer and then intentionally tried to trick you. But did we just clear up the following things? The final momentum of both cups, what's it going to be?
Rest.
They're going to come to rest, so the final momentum of each cup will be 0. The initial momentum of each cup will be mv. Did you just tell me that they both are traveling the same speed when they reach the ground? So the change in momentum of the cups will have to be the same because they both hit the ground at the same speed and they both are brought to rest by the ground. So the impulse they experience is the same because they have the same change in momentum. Remember, impulse is change in momentum. It's not impulse that breaks the glass. What breaks the glass is force. Why does the one that hit the carpet not break? Describe what the carpet is like compared to the tile that makes it so it doesn't break. Cushioning, softer, are those reasonable things to say? Well, it's what cushioning and softening means here in mathematics. The math of this part is about time. The more cushioned surface makes it take longer for the cup to stop. And because it takes longer for the cup to stop, it receives less force. The impulse is the same whether it hits a tile or hits a carpet, but taking longer to stop means it takes less force to do so. The cup doesn't break. But the cup that strikes the tile has to stop in a very short amount of time. So time becomes small. That means force goes up. The quicker we have to stop something, the more force you have to use to stop it. Now,